In the previous video, we defined binary search trees as a special variant of binary trees that satisfy one additional property, which is all elements in the left subtree of a node will be smaller than the root or the node element, and all elements on the right hand side or the right subtree of a node will be greater than the root value or the node value. And this property is recursive, which is it applies for every node in the tree. So that means all elements to the left of 12 will be smaller, and all elements to the left or to the right of 12 will be greater than 12, and so on. In this video, we are going to discuss how useful these binary search trees are in several different applications. We'll also cover how to create your own tree node class or how to create your own binary search tree, followed with a discussion on the common operations which include insertion and search in a BST. So without further ado, let's get started. BSTs, one example where BSTs are really commonly used is, let's say if we want to model a dictionary or store all the words possible in an English alphabet. So in that case, we can define a dictionary where we have a binary search tree where each node stores a string such that like all elements on the left hand side of the string or a node, like in this case lay, will be lesser in terms of alphabet, or all the elements here will be from A to L, and all elements on the right hand side of lay will be from L to Z. So all the words that start from A and N till L will be on the left hand side, and all words that start with L and terminate with Z will be on the right hand side. There are several different applications, and the different trees we are going to cover in the upcoming modules build on top of this property of BST. So let's discuss how we can actually create a BST. So we can define our own C++ node class similar to what we discussed in the linked list section or the previous module. So we can have a class node, or I'm calling this tree node, and similar to the linked list, we can have two additional data members, which is one of them is the value that it is storing, which is in this case, like let's say our value is int. It could be a string, it could be an object, it could be anything. Also, it has, like when we discussed linked list, it had a next pointer to the next element in the linked list. But when we talk about BSTs, each node actually has two different pointers which point to its children, which is if we have a node like this, it has two different nodes which are its left child and its right child. So therefore we need like two different pointers, which is tree node star left and tree node star right. Now there are many different ways to actually represent a tree node. You can use a struct, you can use an inner class in case of C++. We are not going to discuss different types of design, but if you want, like there are additional readings, or also your book might cover a couple of different ways to implement trees. We are just going to stick to the basic version of how trees are defined. So this is an example of the tree node class. So we have an integer value. You can also use like templates in case you want to create a generic tree, and then it will have three different data members, which is one of them is values, the other ones is left and right pointers to point to the left and right children. Also, it has a constructor that basically initializes the value left and right children to nulls or a certain value that has been passed. Now I have the entire implementation of BSTs, the insertion function and the tree node class here. So if anybody is interested, they can check it out. Now let's discuss conceptually how the search and insertion works, and then I'm going to switch to C++ code and show you the visualization of how trees are defined. one of the things you have to note is that like search and insertion work pretty much like really similarly. So once you understand like insertion, you can pretty easily understand search, and once you understand search, you basically understand insertion. So how this works is search is like whenever we are calling the insertion operation, we are basically trying to find or search a node in the tree. So let's say in this case you are given a tree node, and if I tell you to create a function for search, your function might look something like this, which is this function search might take in a parameter which is tree node star root, which gives us an access to the root of this tree. Also, this function might take in another value, which is the key that you are looking for, like which is the element that you are trying to search. So I'm calling this, let's say, key. So the idea of search here is that like if I pass in this tree and a value, like let's say I'm calling the key 14, this function should be of return type boolean that checks whether the number 14 is there in this tree or not. So how this works is you'll start with the root node. Next, you're going to compare if the value at the root, which is root dot value, is equal to key, then you stop, because we have actually found that the key is there in the tree. If this key is not matching the root node, then what we are going to do is we are going to compare whether key is less than root's value or key is greater than the root's value. So if it is less than the root's value, then we'll go to the left side of the tree, because we know that the key will never be there on the right hand side based on the property of the trees. And if it is greater, we'll only go towards the right hand side, which is we'll switch the problem, or we can recursively call the search function with, instead of the root pointer, actually calling it, let's say if we are talking about 14, since we know 25 is greater than 14, we just need to go towards the left hand side. So we can recursively call the search function on the left child of this root node, which is root's left, and we can pass in the key because the key is the same. So next we are going to compare 14 with this number 12. Now we know that 12 is lesser than 14, or the key should be on the right hand side. So we'll pass in to this function search recursively like root's right along with the key that we are looking for. And this process repeats till we have reached the leaf node. So in this case, like let's say if you are trying to search the number 15, then what would have happened is after 14 we'll further traverse towards the right hand side, but since we have encountered a null node, what we are going to do is the first thing, which is for this particular function, we are going to test whether the root is null or not. So if that is null, we are going to return false in that case, because the search is unsuccessful, which is in this case we didn't find the value. So one thing you might have noticed from this is that the search is actually dependent on the height of the tree, which is we are going either towards left or right, and this search is proportional to height of the tree. And if you want to find out what would be the time complexity of this, it would be O of height of this tree. So in the next module, we are going to discuss how we can derive height of the tree. It could be anywhere in the range from 1 to n. Typically for a balanced tree, it's log base 2n, and we are going to cover those proofs later, but that's what's upcoming. But let's discuss like this is the pseudocode for the search operation, which is you search the tree, like if it is empty, that means the target is not found, or you return false in the Boolean method. if the target matches, then you return the data stored, or you return true, because that's what we are trying to find. Otherwise, you see whether the target or the key that we are trying to find is that less than node's data, then you would go towards the left subtree. Otherwise, you will go towards the right subtree. So that's the gist of like search. Now, insertion works exactly similar as a search, which is we are basically trying to search an element which we are trying to insert. So let's say if we have a tree given to us like this. This is the root node, like root is pointing to 25. Now what we can do is we can pass this root node to our insert function, like which takes two parameters, tree node root, and the other one is the value that we are trying to insert, which is like I'm calling this value, let's say insert ID. So let's say if I try to insert in this tree another value like 25, how that works is you like since 25 is already there in the tree, nothing will happen, which is like you can have a mechanism which is earlier when we discussed tree node class, instead of storing the tree node, what you can do is you can also store a variable like int count that keeps a track of the number of same elements in the tree. Like that is one way to solve the problem, which is if you have duplicates, you can have a counter that keeps a track of how many are values are there. Typically, like when you solve problems, what we will assume is that there are no repeated elements in the tree, which is all of the elements are technically unique. And if there is a same value, you can just override it or something like that. So it will be given to you in the question. Otherwise, you have to make some design changes. As I mentioned, like you can have an int count, or what you can do is you can make the assumption that you will go towards the left hand side if the value is similar, and go towards the right hand side if it is greater than or equal to. So these are some ways like you can address this. Now coming back to the question of insertion. So let's say if I wanted to insert another value like which is called 26, what I'm going to do is I'm going to start with the root. I'm going to compare the value to be inserted, like this time it's 26. Like since 26 is greater than 25, I'll go towards the right hand side. Next, I'm going to compare 26 with 51. Since it's lesser than 51, I'm going to go towards the left hand side. Next, I'm going to compare 26 with 34. Now 26 is smaller than 34, so I'm going to attach a new node right here that's called 26, which is towards the left of 34. Now this satisfies the BST property because you see everything in the left is smaller and everything on the right is greater. Now how we do this is I'm going to show you the code, and we'll also see a visualization of this, but I want to take another example. Like let's say if we have an empty tree which consists of nothing. So let's take a series of numbers and try to create a tree which is 5, 15, maybe 25, 6, 1. So how it works is, since the tree is technically empty, we can create a new node with the value 5. Now we have 15. 15 will be attached to the right of 5 because it is greater than 5. 25. So we compare 25 with 5. It's greater, go towards right. We compare 25 with 15. Since it's greater, you attach 25 towards the right hand side. Next we have 6. 6 is greater than 5, so go towards the right. It's lesser than 15, so you're going to attach 6 right here. Next we have 1. So 1 is lesser than 5, and we are going to attach 1 right here. So that's how we are going to insert a particular series of elements in the tree. Now let's discuss the pseudocode, and then we'll discuss the code for insertion problem. So in this case, what we are going to do is we are going to see if the root node is null or not. Like if there's no element in the tree, then we are just going to create a new node, and that's actually pointing to the root, and you're done. Otherwise, we are going to check if the item is equal to root data. Then you return false because maybe this method is actually checking whether the insertion is successful or not. So in that case, you can also return a Boolean value. It could also be like your insert method is of type void. It really depends on the implementation. Also, the specifications will be given to you in the problem. Otherwise, you'll compare if the item that you are trying to insert, if it is less than the root data, you recursively insert the item in the left subtree, or recursively insert the item in the right subtree if it is greater. So here, again, like this points to the actual code for insertion. So let's try to translate this recursive algorithm from pseudocode to actual code. So what you're going to do is you are going to first check if our root is equal to null. So if that is the case, then what we are going to do is we are going to, like, this function is returning the root node of the tree. So what we are going to do is we are going to return a new node. Like, you can do this in separate lines or in the same line, that's fine. New tree node, and you will pass into the constructor the value which is the key, and left and right pointers which are nulls. So that is the base case, which is there are no elements in the tree. Now the second case, I'm assuming that the tree does not have duplicates, or we are not passing in duplicates. But if you have that case, it's pretty easy to handle. So otherwise, what we are going to do is we are going to check if roots value, which is in this case roots val, is that greater than the key. Or I think I should actually use the other way around, which is the key less than roots value? So if that is the case, then we have to move towards the left side in the tree, which is like, if let's say if we have a 10 and we want to insert the value 5, now 5 is less than 10, so we have to move towards the left hand side in the tree. So what we are going to do is, since this function returns a root node, we need to recursively call this method insert, but this time we have to pass in the left hand side or the left subtree. So what we are going to pass is we are going to pass roots left in the insert, followed with the key value, which is in this case the function is comma key. And here we are going to, like, since this function is having some return value, we are going to append this to roots left, which is roots left will actually be equal to the new subtree that is created on the left hand side. So we are kind of like delaying the problem. Otherwise it will be like pretty symmetrical, which is in the else clause we'll have something like root right, which is equal to insert root right comma key. So let's see the exact code here, which is again we check whether the root is null, you create a new node. Otherwise you compare, like, is key less than root value. So in that case we insert the left insert the key in the left subtree by using this terminology, or we insert the like, if the case is that the key is greater than the roots value, then we insert it in the right subtree. So I'm going to show you a visualization of how this insertion is actually working in the recursive call stack. Maybe first we can see it in a small example here, and then we can see the visualization, and then we'll discuss the next operation, which is deletion. So how the visualization might work is, like, let's say if we have a tree here that's like 10, 5, I'm just taking some arbitrary values. Let me just move the tree somewhere else. Give me 1 second. Yeah, so let's draw another example. So we have like the number 10, we have 5, we have let's say 15, and let's say we have one more number, which is like, let's say 7. So in this case, how it's actually working is like we pass this root node into this insert function, and let's say if we are trying to insert a value, let's call the value like 4 maybe. Okay, so how this works is the root is actually compared to null, so in that case it's false, so it will go to the next statement, which is key less than root value, which is 4 less than the value at the root, which is 4 is being compared with this root value, which is 10. Now since 4 is lesser, we'll execute this statement, which is roots left is equal to insert roots left with the key, or we are inserting the key in the left subtree. So how this will work is it will recursively call the insert function with roots left, which is now the new root will become this one, 5. And we'll pass in the key value, which is 4. So once we recursively call this function, it will go back up. It will compare 5 is equal to null, or the tree rooted at 5, is that equal to null? If that is the case, like that's not the case, so it will go back right here. It's going to check whether the key is less than root's value, which is key is now 4, and 4 is less than root's value, which is now the root's value is actually 5, because we are in a different stack frame. So initially we called this with the first time we called it with the roots rooted at 10 and the key was actually 4. Next time it's actually the new root is 5 and the key remains the same, which is 4. So these are like different stack frames. So 5 and 4 are being compared, so 4 is less, so we are going to again execute this left statement, which is roots left is equal to insert root left, which is now we are going to pass in roots left, which is now in this case null. So in the stack frame we'll have another function call, which is null comma 4. So when we call null comma 4, it will go back up. It will check whether the root is equal to null, which is true in this case. It will now actually create a new tree node with the value key, which is 4. So a new tree node is now created, and this is returned to the previous function call. So you remember we have root left on the previous function call, which still has to be executed. So what will happen is this new node that's created, like this 4 one, will be attached to this 5 node which was in the previous stack frame. So roots left will now point to 4. Now that means this function has terminated, and like if we go back to this function, although we have executed this statement, it will still keep going and return the root, which is in this case like roots left, which is 5. So the tree is rooted at 5, so it will be returned back to the previous function call. So in that case, since 5 is returned back to the new tree is being returned back to the original tree's root, which is 10 in that case, so this will automatically be attached. So that's how the recursion is working, and I can just show you a quick demo on how this is working, which is you can copy paste this code in Python tutor. Like this is the version of the code. I have some values, which is 50, 20, 14 and 22, and I'm going to show you how the visualization is going on in the stack frames. We won't be able to cover the entire thing, but I can show you for 2 nodes maybe, because I don't want to make this video longer. But if you have already understood this concept, we are going to terminate the video right here, which is the insertion part. So feel free to watch the deletion video if you have already understood it. So let me discuss how this works. So initially our tree node like is exactly the same as we just saw. We defined the root pointer to be null, and now what's going on is we are going to call the insert function with our root and the value 50. So it starts right here, and what happens is it goes to the insert function. Our root is null, so it will create like it will go to the next statement, which is root null, which is true. So it will create a new node, like, so it will go to the 9th line here because it's creating a new node with the value 50 and left and right pointers that are both nulls. So we create kind of a new node here, and this one is actually returned back to the main function. So after the execution, we have just one node, which is like this. So root is pointing to one node, which is 50 with left and rights both nulls. Next, we insert root with value 20. So root is still pointing to this. Now what will happen is you're going to pass 20 here. So it will go back to the first line of the insert function. It's going to check is root equal to null, which is now false, as we all know. It's going to compare the key value, which is key is 20, with the root value, which is in this case 50. So since it's less, it will actually execute this line 19, which is root left equal to insert. But now, since this is a recursive call, there'll be a new stack frame. So we have another stack frame here. Here, the root will now point to the insert values root, which we passed in, which is roots left. So the new stack frame's root is actually not pointing to the original root, but the roots left, which is in this case null. So you're going to see the root is actually pointing to null. The key is again 20. At this case, like since root is equal to null, it will generate a new node, which is the tree node with the key value 20 and the root actually pointing to this new node, which is 20. So that is being getting, like, let's see, which is we just created a new node, and here you can see that after the execution of this function, that gets attached to the left side of 50. Next, it will go back to the main function and it will try to insert the 14. So it's again the same process, which is it will first go back up. It will check if the root is equal to null, which is false. So it will check whether 14 is less than 50. Yes. So it will go towards the left hand side and a new stack frame will be created. Now we are right now pointing the new stack frame's root is actually pointing to the original roots left, which is this node. So it's going to point to this node. Next, we are going to compare 14 with this 20. So since 14 is less than that, again a new stack frame is initialized with the root pointing to null, because you are pointing the current nodes left into this root node and with the key value 14. So now, since the root is null, a new tree node is created with the value 14, and this will be returned back to the previous call. So previous function call. So that's why it's getting attached right here. So finally, we have one last one, which is for the next number, which is 22. I'm going to provide you this code, and I would strongly encourage to, like, if you do not understand how recursion is working, to trace through the program and see how it's executing in action. Because, like, let's say if you try to insert 22, what's going to happen, like, is it's going to compare 22 with 50, and now it will compare 22 with 20, and then it will compare like 22 with null, which is on the right. So it will create a new node right here. So as you can see, which is, if I skip through the program, I'm going to skip through because we have less time. You can see that after the execution, we'll have one more new node, which is pointing to the right of this. So our tree would look something like this. That's pretty much it for this video. Insertion, like there is a stepping problem on the insertion. Try that out. It's important that you understand the fundamentals well, because otherwise you won't be able to build on different operations. Also, the project requires this knowledge because technically the project is on the project uses trees, so you'll require this knowledge to build different functions in the tree. Thanks, and let's move to the next video, which will cover discussion.